Swayam Prabha. Digital India. Educated India.
Good morning. This is the third lecture on axial flow compressor. The contents of the lecture are degree of reaction for a stage, losses of a compressor stage. Here I'll discuss about the profile loss, annulus loss, secondary flow loss, tip clearance loss, and the correlations. Degree of reaction for stage. To initiate the discussion on degree of reaction of a stage, let us consider the flow past a stage is incompressible and isentropic, that is reversible and adiabatic. Here I have indicated the velocity tangles at inlet and exit of a rotor, where u is the blade speed and w being the relative velocity and c is the absolute velocity and beta is the relative air angle and alpha is the absolute air angle. The subscript 1 represents inlet and 2 for the exit. I have illustrated all the velocity triangles before. Now, the degree of reactions of a stage is defined as the ratio of ideal static pressure rise across the rotor to the ideal pressure rise across the stage. Now, the work absorbing component for the stator is 0. Thus, the R can be stated as the ratio of ideal static pressure rise to the ideal total pressure rise across the rotor. Now look, for a compressor, the relative velocity decelerates. Now if we consider a streamline that is passing through the central plane between the two neighboring blades, then the ideal static pressure rise across the rotor can be stated as half rho W1 square minus W2 square. And ideal total pressure rise across the rotor can be equated to the Euler work rho u c theta 2 minus c theta 1. Thus R can be written as half rho within bracket W1 square minus W2 square divided by rho u c theta 2 minus c theta 1. Now, from velocity triangle, W1 square is equal to W theta 1 square plus WZ square. Similarly, I can write W2 square is equal to W theta 2 square plus WZ square. Put the value of W1 and W2 over here. And furthermore, c theta 2 minus c theta 1 can be written as W theta 1 minus W theta 2. Therefore, the degree of reaction becomes R is equal to W theta 1 plus W theta 2 divided by twice U. Now again from the velocity triangle, W theta 1 is equal to WZ into tan beta 1 and W theta 2 is equal to WZ into tan beta 2, where WZ is the axial component of relative velocity, so WZ must be equal to CZ. So putting the value of W theta 1 and W theta 2, the degree of reaction R can be stated as Wz by U within bracket tan beta 1 plus tan beta 2 divided by 2. Now Wz by U is the flow coefficient phi, and tan beta 1 plus tan beta 2 by 2 is nothing but tan beta m. Therefore, degree of reaction R can be stated as, for incompressible and isentropic flow, R is equal to phi into tan beta m. Thus, we have R is equal to phi into tan beta m, equation number 24, where R is the degree of reaction, phi is the flow coefficient, and beta m is the vectorial mean angle. Equation 24 gives the degree of reaction of a stage when the flow is considered as incompressible and isentropic. I have projected as before the inlet and exit velocity triangle of a rotor. Now I can write flow coefficient phi as Cz by U. U can be written as, U is the blade speed, can be written as W theta 1 plus C theta 1. Now using the velocity triangle, the phi would be 1 divided by tan beta 1 plus tan alpha 1. Similarly, I can write phi is equal to Cz divided by W theta 2 plus C theta 2, which can be equal to 1 divided by tan beta 2 plus tan alpha 2. Again, using the relations for degree of reaction, equation 24, and assuming R is equal to half, we have half is equal to phi into, within the bracket, tan beta 1 plus tan beta 2 divided by 2. Therefore, from here I can write 1 by phi is equal to tan beta 1 plus tan beta 2. Let us imagine this is some equation as A, this must be equal to B, and this must be equal to C. So if you equate equation A and C, I'll get this relation. And similarly, if you equate the equation B and C, I'll get the second relations, right? So I have got two relations, that is tan beta 1 plus beta 2 is equal to tan beta 1 plus tan alpha 1. Now this beta 1, tan beta 1 will cancel out from both the sides. So what I'll get? Alpha 1 is equal to beta 2. And from the second relation, beta 2, tan beta 2 will cancel out. I'll get beta 1 is equal to alpha 2. Thus, for degree of reaction is equal to half, I have got the following two relations, that beta 2 is equal to alpha 1 and beta 1 is equal to alpha 2. Come to the velocity triangle. Imagine here that this beta 1 here, for when the degree of reaction is half, beta 1 here would be equal to alpha 2, and beta 2, this angle would be equal to alpha 1. Thereby, the inlet and exit velocity triangle are the mirror image of each other. Hence, for the 50% reaction stage, the velocity triangles are the mirror image of each other, and thus the rotor and the stator blades are symmetrical. The static pressure rise in the rotor is same as that of the stator. Furthermore, the boundary layer growth, loading are the same and the losses are also the same for the both rotor and stator. So thus we are leading to the repeating stage. Nowadays it has been realized that the rotor can withstand higher pressure rise without excessive losses. Hence, we may seek for a higher degree of reaction. Furthermore, one can remember that xi is nothing but c theta 2 minus c theta 1 divided by u, or it can be written as w theta 1 minus w theta 2 divided by u. For a compressor, phi is equal to cz by u, and r is equal to w theta 1 plus w theta 2 divided by twice u, or r can be written as phi into tan beta m. With respect to degree of reaction, a more general definition can be given for compressible and irreversible flow through a compressor. Thus here, the degree of reaction is defined as the ratio of static temperature rise to the rotor to the static temperature rise to the stage. Thus R I have written here as static temperature rise in rotor divided by static temperature rise across the stage. It should be noted that we can arrive at the same expression considering the flow as compressible and irreversible as R is equal to phi into tan beta m. Thus, the equation 26 gives the expressions for degree of reaction for both compressible and incompressible flow. Now I'll discuss on losses of a compressor stage. The total losses can be subdivided into the following categories. The one is the profile loss on the blade surface, which can be evaluated from casket test. The second is the skin friction loss on annulus wall. The third is the secondary flow loss, and the last one is the tip clearance loss. Thus, the total loss coefficient can be defined as CD is equal to CDP, CDA, CDS, and CDT, where CDP is the profile loss coefficient, CDA is the annulus loss coefficient. Similarly, CDS is the secondary flow loss coefficient, and CDP is the tip clearance loss coefficient. The profile loss is because of the boundary layer development on the blade surface due to the viscous flow. I have indicated a pictorial view here illustrating the development of the boundary layer and the formation of oil behind the blade by the shaded region. Thus, the boundary layer on the blade surface attributes to the appearance of oil behind the blade, and because of formation of boundary layer on the surface and the formation of oil, what will be the resultant? That there will be a decrease in total pressure due to frictional loss on the blade and mixing of wax. These profile losses can be appreciated from casket test. The origin of secondary flow is the formation of boundary layer on the hub and casing and the distortion of this boundary layer within the blade passage forming passage vortex as indicated in this figure here. In this figure, I have illustrated the formation of indwell passage and counter vortex due to rolling of boundary layer at the leading edge of the blade. Thus, the formation and secondary flow and associated losses I have illustrated here pointwise, stating that the occurrence of passage vortex due to the distortion of inlet boundary layer while passing to the car passage is well known. However, the rolling up of indwell boundary layer in front of the leading edge into a vertical motion called the horseshoe vortex has given a new dimension to secondary flow concepts. The passage side leg of the horseshoe vortex has the same sense of rotation as the passage vortex, while the suction side leg of the horseshoe vortex, called the counter vortex, rotates in the opposite sense to the passage vortex. Now let me explain about the effect of secondary flow. Now secondary flows are an important source of loss in turbomachinery. We'll have to live with secondary flow. However, we should know how to minimize the secondary flow losses. Now here, the secondary flow vortices tend to redistribute low momentum fluid from the pressure side to the suction side of the blade passage, attributing to significant mixing losses. Thus, the main losses of secondary flow is the mixing loss because of redistribution of momentum from pressure side to the suction side. Now, let us appreciate the tip clearance loss. This loss arises due to the clearance between the moving blade and the casing. Now, because of the static pressure difference between the suction and the pressure side, flow leaks from the pressure side towards the suction side, affecting adversely stage efficiency and the mass flow rate. Furthermore, the leakage fluids develops tip leakage vortices, a region of complex flow and significant mixing. Thereby, the tip leakage vortices, which is also a cause of significant mixing, creates losses. I have illustrated here the effect of tip leakage vortex through some figures or schematic. I have indicated here a series of blades where, because of tip clearance, fluid leaks from the pressure to a suction side, forming tip leakage vortex. A chain of vortices has been illustrated here, and because of this tip leakage vortex, also the pressure distribution on both the suction and pressure side has been affected. And look here towards the second half of the suction surface, the adverse pressure gradients is much steeper with tip leakage vortex. Now, with respect to annulus loss, The annulus loss is associated with the hub and south wall boundary layer between the blade rows, and it can be closely related to the secondary flow. Following correlations have been established for annulus loss coefficient, secondary flow, and tip clearance loss, while for profile loss we depend on cascade test. Thus, through cascade test, CL, that is lift coefficient, and CD, the drag coefficient, is established apart from total pressure loss. Thus, CDA is equal to 0.02 into S by H, where S is the pitch of the blade and H is the height of the blade. Similarly, CDS is equal to 0.018 CL squared, where CL being the lift coefficient established from cascade data, and CDT, that is tip losses, is proportional to T by H CL to the power 3 by 2. T is the tip clearance, H is the height of the blade, CL is the lift coefficient. Here in this figure, I have indicated the compressor stage losses and thus the estimated efficiency. At the design point, I have illustrated the proportional loss. Suppose the annulus loss would be 2.2% at the design point. The secondary flow loss would be 4.4%, and furthermore profile loss would be 4.2%. Now it should be noted that profile loss dramatically increases after certain value of flow coefficients. Thus, if I increase phi, the contribution of profile losses would be much higher corresponding to other two. Thank you for listening.